I'm Dr. T and welcome to my office. So today I would like to talk about heat and temperature. And when it comes to these two terms, we typically like to think about them as the same thing, but fundamentally they are, while related, definitely different topics. So temperature is a look at the atoms, how fast they are vibrating. And I will point out that this is a somewhat oversimplified view, and most of my talk will be just a little bit oversimplified. But you're looking at what is essentially the average kinetic energy of all of the atoms in your thing. And that's its temperature. Now, heat is the energy going in to add to that or subtract from it. You don't measure heat as a sum total. It's always what's flowing back and forth. It's essentially like work. And in fact, we quite often will say the energy that's being moved around is the sum of the work, which is orderly motion of things typically, and that of the heat, which is this kind of disorderly motion, which is causing these atoms to get bumping around even more. Heat counterintuitively gets the symbol Q. Historians have just kind of been like, wait, what? Late 19th, early 20th century, I think it was late 19th century. German researchers said, hey, we're going to give, in my paper, heat a variable, we're going to call it Q, and everyone's like, okay, heat's Q. And since then, it's like, wait, why? But anyways, so we've got heat. It is an amount of energy going in or away from a system. And when I say system, I just mean whatever we're talking about. So if I got a cup of water that I'm heating up in the microwave, the cup of water is the system. Everything else is what we call the surroundings. Okay, now those two are related, and we can relate them by an equation that I will try and stick there. This is sometimes referred to as a calorimetry equation, and this has some fairly straightforward parts. So Q is the amount of heat, once again, Y, and that's going to equal the amount of stuff you have. Because if you imagine, if you put some heat into something, if I put the same amount of heat into a teacup versus a swimming pool, yeah, that teacup's going to get really hot, and that swimming pool, you won't know you did anything. So the amount of stuff you have matters. So if I'm trying to raise the temperature, I'm going to add heat, and, well, the more stuff I have, the more heat I'm going to have to add. Or, conversely, take away heat, if I'm trying to cool it off. Then the next term is what's known as specific heat. I usually see it as C sub S. And this is basically a constant. This is converting the units for heat, which, like all energy, is done either in joules for the SI system, but you can use other things like calories and whatnot. And so this is going to convert that into units of mass and of temperature. Now, this is not a fixed constant. So in some equations that we deal with, there's a constant that's just a universal, it is the constant. But in this case, specific heat is relative to every specific thing. And in fact, it actually varies depending on the temperature, just to make life even more complicated. So if you've got a thing, a substance, your system, depending on what it is, your specific heat will be different. And that does have some rather interesting consequences. So if you go out to the desert, those are famous for massive temperature swings. And that's because the specific heat of soil is fairly low. So it doesn't take that much heat to warm it up to really hot during the day. And then at night it gives off the heat, and, well, it cools off quick because it doesn't have that much heat to give off. Whereas if you go to a nice ocean area, water has a very high specific heat. And so it takes a lot of heat to heat that up and raise the temperature. So it doesn't get very hot during the day. The temperature can't go up that high. And, well, at night, it's got all this heat to give off, so the temperature doesn't drop very low. So it acts like this buffer. And that's what you see in areas that are governed by large amounts of water, like, San Diego. Beautiful weather. Horridly expensive cost of living. Everyone wants to live there. I mean, it is beautiful. Don't get me wrong. But if you go to, say, the high desert, someplace like Phoenix, the temperature swings like crazy. Okay, so we've got this equation, and then the last part, of course, is, well, how much does the temperature change? So this is going to be delta T. So remember, delta means change, and then capital T means temperature. Lowercase t means time, because of course, we have two important things, both start with a T. And unlike heat, we actually, started them with a letter that makes sense. Now, when we're looking at this, interesting feature is heat is basically impossible to measure by itself. You can measure a temperature change fairly easily. You can measure a temperature pretty easily, but the heat itself is basically unmeasurable. So you use the aforementioned calorimetry equation to measure that heat. And we can do some interesting algebra with this, such as set two things equal to each other. You have to put a minus sign in it in order to account for the fact that heat is flowing one way or another. And you can do that if you're looking at a hot thing warming up a cold thing kind of scenario. Now, how do we actually measure temperature? And we've got a couple of approaches to this. We can use what's known as thermal expansion. So as things warm up, their atoms bounce around a little bit more, and they tend to take up a little bit more space. And so things will get slightly larger. For most applications, this isn't really much, but a little bit can start adding up. I used to live in Yuma, Arizona, and there, going to work, there was this stretch of sidewalk that was literally a mile long, just straight, uninterrupted stretch. And what would happen is, in the summer, when it's 120 degrees out, because Yuma, the sidewalk would expand, and there was a part in the sidewalk that would buckle, and it would seriously go up about 4 to 5 feet, where two segments of the sidewalk would be pushing against each other, and it would just buckle up because that tiny amount of expansion, but over the course of, I believe it was a mile, if not more. It was this really long sidewalk that really needed some curves in it. So this can add up. If you look at the old-timey clocks, the ones with the pendulums that go back and forth, they have really weird pendulums, and that's to account for thermal expansion. Now, back to actually measuring temperature. So some of the early thermometers, what those would do would look at thermal expansion of some kind of liquid that would then flow up the tube. The liquid that tends to work the best is mercury. Now, to have the thermal expansion be enough to really be meaningful, you have to have a very, very tiny tube, which is good, so you don't have to use that much mercury. Unfortunately, while these work beautifully, I love a good mercury thermometer. If you drop them, they're a hazmat spill. So we've basically phased out of mercury thermometers. You rarely ever see one of them. You can simply swap out the mercury for alcohol. New thermometer, you can't just replace it. But you can swap out mercury for alcohol. It does not work as well at all. But it still definitely works, so you can do that. Alternatively, here in the 21st century, we've taken a couple other approaches. When atoms vibrate, they can take that vibrational energy, and instead of just bouncing around, they can convert that into a photon of light that's in the infrared range. And so if you have what is essentially an infrared camera, you can measure the amount and wavelength of the infrared light coming off the surface, and that will tell you the temperature. Obviously, if you get hot enough, you get enough bouncing around, that color will actually turn into visible spectrum, and you get higher and higher energy photons. But for most things that aren't so hot they are literally glowing, you're looking at infrared, because really everything does glow in the infrared. That's how the modern kind of forehead and ear thermometers work. That's also how a lot of the night vision and some snakes see in the dark kind of scenario. Another approach that's also very, very common is if you have two strips of metal that are not the same metal, but they are smushed together, so they're fused together, so they're now one thing. The electrical properties of those metals change depending on the temperature, so you can look at how that electric current runs through them. Or, oddly enough, you can look at how much they expand, and that's how those coil thermometers work. So you've got lots of approaches. Those are just kind of the top ones of ways of thinking about it. Now, when you're looking at units for temperature, obviously we're familiar with Fahrenheit and Celsius, aka centigrade. It's the same too. Celsius, centigrade, same thing. These are both what we call relative scales. So they have an arbitrary 0 point. For Fahrenheit, it's an argument of what that 0 is actually there for. It is either the freezing point of seawater and or it's as cold as where Fahrenheit, because this was named after a guy, lived. As cold as it ever got there. So either way, they're about the same. And then they have an arbitrary 100-degree point. So for Celsius, the arbitrary 0-degree point is the freezing point of pure water. Now, the arbitrary 100-degree point for Fahrenheit is really arbitrary. So one argument is it's body temperature, but everyone was running a fever. Alternatively, it is as hot as it got where Fahrenheit lived. For Celsius, it's the boiling point of pure water. Now, for both scales, this is actually quite a problem because those numbers are truly arbitrary. For water, it has some definite meaning, but for everything else, those are arbitrary numbers. And if we want to use those in equations, we're going to run into problems. So quite often what we want to do is what's known as an absolute scale. And what an absolute scale is it starts at absolute zero. The point where temperature is as cold as it can get. You know, you're measuring average kinetic energy, asterisk. It's a little bit more complicated than that, but it's a fine working definition. And well, what happens when average hits zero? Well, at that point you have zero. So at negative 273.15 degrees Celsius, or I'm probably going to get this wrong, and there'll be a thing somewhere over here saying what it really is, negative 413 degrees Fahrenheit. You can't go colder. So what you can do is you can use the units that you've already set up and been using, but instead of putting the zero at an arbitrary point, you put it at absolute zero. For Celsius, if you do that, you get Kelvin. Side note, contrary to what the light bulb manufacturers keep putting on, there is no degree sign if it's an absolute scale. So Celsius and Fahrenheit get degree signs, Kelvin does not. Fahrenheit has a cousin, which is ranking, that like no one uses anymore. Kelvin has won in that particular race. So with that said, have a wonderful day.